Alright, so today we're looking at section 4.1. This is question number 10. And what we're looking for is critical points, domain endpoints, and local extrema. And this is the graph that we are investigating. The first thing that's important to note is finding out where this graph can be while the y, so what values of x it can have, while still allowing y to be an element of the real numbers. So we want y to be an element of the real numbers. And so we don't want any complex numbers, which means we can't take the square root of any negative numbers. And what you'll notice is if I put any number in here bigger than 4, what we'll end up with is a negative under the radical. So I cannot have numbers bigger than 4. And you'll also notice if you put negative number that's slightly less than 4, like say negative 4.1, you'll end up with a negative under the radical as well. So, and we could solve for this as well by saying 16 minus x squared is equal to 0, because we're interested in the points at which it is equal to 0. So we would end up with x squared equals 16. The square root will be plus or minus 4. So that's where our domain points come from for this particular graph. Of course, 4 is included because if we plug in 4 here, we just end up with a 0 under the root, and we can do that. So I'm including them in the domain. The next step, when finding extrema and critical points, is to take the derivative of the function. So dy dx equals first derivative of the second. I'm going to write this to the 1/2. First is 4x. The second is 1/2 16 minus x squared to the minus 1/2 per the power rule, and then multiplying it by negative 2x per the chain rule. And then we add second d first. So that's 16 minus x squared to the 1/2 times 4. The derivative of 4x is 4. 4 times 16 minus x squared all to the 1/2. And now let's go ahead and simplify. So 4 divided by 2 is 2. 2x times negative 2x is negative 4x squared. And that's all over the top of the square root of 16 minus x squared, because this is to the minus 1/2, so it's a root in the denominator. Then we're adding this, we're adding 4 times the square root of 16 minus x squared for this term over here. And with extrema points, we set them equal to 0. And the reason why is, let's say that we have a graph like this. So when we're looking for extrema, we're talking about local maxima and minima. And what I mean by local is, for example, Mount Denali in Alaska would be a local maximum, even though Mount Everest is taller. So in other words, to be a maxima, a local maxima, you don't need to be the tallest thing in the whole graph. You just need to be the tallest thing with reference to the areas you're around. So that's a local maxima right here. That's a local minima. And what you'll notice is that the graph does actually get higher than this local maxima and also gets lower than this local minima. But that doesn't change the fact that these are the local minimum and local maximum. Maybe this graph goes all the way up to positive infinity. So its absolute maximum would be positive infinity. Its absolute minimum would be negative infinity. But then beyond that, it would have 2 local maxima and minima, or 2 critical points. So anyhow, the important thing about that is that if you take a slope at any given point on the graph, tangent to the graph, you'll notice that when you get up to the top of a mountain or to the bottom of a valley, that the rate of change, the slope at those points is always 0. The tangent lines to maxima and minima always have a slope of 0. So that is why we set our derivative equal to 0 to find critical points. And now we'll solve for it algebraically. Let's add this term over here. 4x squared over square root 16 minus x squared equals 4 times the square root of 16 minus x squared. So right away we see that we could divide both sides by 4 and get rid of the 4's. Then we could also, we could multiply the 16 minus x squared over here on both sides times root 16 minus x squared. That would cancel it here. And then also what would happen is two square roots of the same thing are going to equal that thing not under the square root. So that's what we're left with. Then we will add the x squared to both sides, and we'll end up with 2x squared equals 16. So then we'll divide by 2, and that'll lead us to x squared equals 8. So if we take the square root of both sides, you'll notice that we're getting two local extrema. One of them is x equals the square root of 8, and the other one is the minus square root of 8. So these are our two x values for our minima and maxima. Another important thing to look at here is, so these are local minima and maxima. We don't know which one it is yet. There's several ways to solve for that. I'm going to do it by plugging in the values. So anyways, the first question asks, what are the critical point or domain endpoints where f prime is undefined? Which is an interesting question. So let's look back at what dy dx equals. And whenever you hear undefined, I want you to be thinking, what numbers would cause me to divide by 0? So if you notice down here in this term, if we have a plus or minus 4 that we plug in as the x value in our derivative, we'll end up dividing by 0. And that's undefined. And the reason why it's undefined is because those are our domain endpoints. And if you remember, to find a true tangent line, you need to not only have the left-handed limit, but the right-handed limit. So because those are the endpoints, it can have a one-sided limit, but it cannot have a two-sided limit, and therefore it's undefined in our derivative. Even though it was part of the domain of our original function, the domain of our derivative does not include minus 4 and does not include 4. And so what that tells us is that for part A, running out of room up here, that the two important points where the limit is not defined is x equals minus 4 and x equals 4. So then part B asks, what are the critical points where f prime is equal to 0? So we solve for those down here. So this is part B. Those are the critical points where there is a definition of the derivative at that point. That's what we solve for, because those have both a left and a right-handed limit. And then part C asks, the points corresponding to the local maxima are blank. And so for that, I would say, I'm going to make some space. So we have an idea of what our critical points look like on this graph. So here's what we know about the graph. We know that the domain is between x equals minus 4 and x equals positive 4. We know that we have critical points at square root 8, so at x equals square root 8, and also at x equals minus root 8. So what I like to do, there's a way to do this with the second derivative, but for me I would just prefer to plug in these values to our original function. So y equals 4x times the square root of 16 minus x squared. So let's plug in positive root 8. Positive root 8 squared is 8. 16 minus 8 is 4. And so what we end up with is y equals 4 times square root of 8, we're plugging that in for x. And then we're multiplying that by root 8 squared is 8. 16 minus 8 is 8. And so we end up with multiplying that by root 8. So this is our y equals, this is our output when our input is positive root 8. Root 8 times root 8 is 8. 8 times 4 is, let's see here, 1632. Sounds right. Okay, so we know that at square root 8, our y output is 32. And so that looks like a maximum. We'll have to check out the other points, though, to figure out if it actually is. So when we plug in y equals square root of, or negative square root of 8, now we have 4 times negative root 8. And then inside of this radical, negative root 8 squared is 8. So 16 minus 8 is 8, so we're multiplying that by positive root 8 again. So now we have a minus 32. And so that tells us that for the point x equals minus 8, that we are at y equals minus 32. So we're starting to get a picture for what this is. We know that when we plugged in 4 to this function, we got 0, and when we plugged in negative 4, we got 0. So we're starting to build a picture of what this function looks like. And that's what it looks like. So it's pretty clear that this is a local maxima at root 8, and this is a local minima at negative x equals negative root 8. So for the maxima, and it's asking for the ordered pair of the points that are the maxima, so that means that we have x, which is root 8, and when we plug in root 8, we get 32 out. So we're just writing the ordered pair for this maxima point. For our minima, we plugged in negative root 8 in the x, and we got out negative 32. And you might think that we're done at this point, but there's a few things left. Okay, so if we were to look at this point when x equals minus 4, does it seem relatively high or low compared to its surrounding points? So we'll notice as we're going to the right here, the values for y drop. So if you were down here, you would think this was a mountain. And so for that reason, that's also a local maxima. That's when x equals minus 4, y equals 0. And likewise over here, if you were standing right here, you would think that was a valley. So that's a local minima. And so the local minima there is when we plug in positive 4, and we get out 0, which is interesting. So even though both of these ones' outputs are 0, they're still relative maxima and minima, which we call local maxima or minima. And so at that point, I believe this includes part C and D. And I think that's the whole problem. So I know this was a long video. Hopefully it helps, and I'll see you next time.